Having seen that we can imagine the average value of a function as one particular y value that has the property that the area of the graph above that average is a perfect match with the area below it, which in this case it isn't actually. So if the graph were to change a little bit here and do that, maybe go a little bit higher, there we go. So shorter but bigger area, longer but thinner area. This average value A can be computed. Well, actually we can do a nice rectangular approximation here. We have a rectangle here that's A times, well, what's the width of this bottom here? It's going to be B minus A. So we have the area of a rectangle is going to equal the area under the graph. This is another way to come up with the average formula under the graph. And the area of this rectangle is the average value spread over B minus A. And that's going to equal the integral from A to B of our function, or the area underneath the graph. And we can simply solve for the A value. 1 over B minus A, 1 over the interval length we're considering, and then we scale that by the actual area under the graph. And that becomes a compact formula, seen here, that lets us compute the average value of a function on a given interval. Let's apply that with a couple of examples. Here, we're asked to compute the average of a temperature, which is varying as a sinusoidal, so it has some kind of cyclic behavior, pretty reasonable for a temperature in a house. And we're going to measure it T in hours, H in degrees, and if we're looking for the average temperature, it'll be also a degrees Celsius thing. So let's do a quick sketch of the graph. It is a sine function which has an 18 added to it, so 18, this is H, this is T, and we have an amplitude of 4, so that's our amplitude, so it'll go up to 22 and down to 14 degrees. It's a sine function, so it's going to start at its average and then go like this and like that, and that looks pretty good until the end. There we go. So that would be our curve. Now, what's the scale on the horizontal or time axis? Remember that the period of a sine function is 2 pi divided by the multiplier for t, which in this case here is pi over 12. And if we sort that all out, pi's cancel, 2 over a 12th is exactly 24 hours, again, which makes sense for a daily cycle. So we have some pattern that repeats itself every 24 hours. Now, if we were asked the question, what's the average temperature over one cycle? Well, based on both our intuition and the analysis we just did, the area above the line y equals 18 or h equals 18 would balance off with the area below. And so 18 would be our average temperature on that 24-hour cycle. However, we're asked for the average on the first 12 hours, which only gets us to here. And if we focus our attention on that part of the graph, it's pretty clear the average has to be between 18 and 22. And probably, well, it's hard to say, maybe a little bit above halfway, because then we get a little more area in this little triangle here, triangle-ish shape, and it looks like we might get a balance of area above the average and area below the average. Well, rather than worry too much about the graphical details, why don't we use our new formula for computing averages and see what it tells us. So what do we have? We have our upper limit, that's B, and it's 12 in this case, and our lower limit is A, and that's 0 in this case. So we're spreading the temperature distribution here over the first 12 hours, so we get a 1 over 12 factor. And then we're going to multiply that by the integral, or the accumulation of h over those 12 hours, and we can just plug in our formula here. 18 plus 4 sine of pi over 12t dt, close bracket. So we're going to take the area underneath this graph, and we're going to spread it out, so include this whole thing down to 0. This is the other way to think of averages. We're going to take the area underneath this graph, and and then we're going to redistribute it so it's flat, and that flat value that would be equivalent or give an equivalent area is what our average height is. Okay, let's do the calculations. We'll have 1/12, and we can actually go and do the integral right away. The integral of 18 with respect to time is 18t, plus 4, the integral of sine is negative cos. We differentiate cos, we get negative sine. We need another negative then. Pi over 12t. All of that divided by pi over 12 to make the constants work out. If we differentiated this, we would get a pi over 12. We need that to cancel, so we just have our 4. Close that bracket, and we're going to evaluate that at 0 and 12 hours. Okay. So that gives us 18 over 12, better known as 3/2, t, plus 1 over 12 times 4, and minus. So we're going to have a negative here. Actually, I have a whole bunch of constants. Let's be clear about this. We're going to have negative 4 over 12 times 12 over pi. Oh, that's not so bad. Okay, those cancel. And we've taken the negative already. So we have cos of pi over 12t between 12 and 0. So it's well worth tidying this off before we go to sub in. And this should represent our average value. Again, it should be a number between 18 and 22. Let's see what we get. 3/2 times 12, plugging in the upper limit, minus 4 over pi cos of pi over 12 times 12, that's cos of pi. That's the upper limit, subbed in. Minus the lower limit subbed in. Well, 0 for t gives us 0 for that term. Minus 4 over pi and cos of 0. Which of these values do we know? Cos of 0, much better known as 1. Cos of pi, much better known as minus 1. And so we're going to get 36 over 2, which is, hey, there's our 18. And if you actually look at how this works, we're spreading 18 over the interval 0 to 12 and then dividing by the 12. And then the sine function is just the varying part. That's being handled by this separate calculation. So it's not a huge surprise that we get 18 back here. Then we get plus 4 over pi, and a double negative again, plus another 4 over pi. So we do get a value above 18, and that value turns out to be 20.54, and again, units, degrees Celsius. The average temperature is a temperature value, and it's going to be just a hair above, or about 0.5 above the 20 line. So pretty much where we sketched it here. And that's an average value calculation using the formula for average values. Let's turn it around a little bit in this example. What if we're given the average and we're trying to compute something else? Well, can't hurt to draw a diagram as this stuff is still new. What we've just been told is that if we were to spread our function around over the interval from 0 to 3, we would get this area here. So our function could be, the area underneath our graph would be equivalent to the area underneath the graph of y equals 5, the average value on the interval 0, 3. So our function could do who knows what. Well, no, it can't do that because it has to have the same area above and below. Well, what does that tell us? Well, the integral from 0 to 3 of f of x dx has to equal the area underneath this graph. So some people might just see it and call it 15. Or we could work backwards and use our average value here and say that the average is 1 over 3 minus 0, the integral from 0 to 3 of f of x dx. This is what we want to find. We know that this is equal to 5, and so we get 5 times 3 is the integral from 0 to 3 of f of x dx, and that, of course, is just 15. For a lot of the questions in the assignment, though, it really helps to have this graphical sense as well as the purely calculational approach to dealing with average values.